Hello and welcome to the very final episode of CS350 Online. That's number 24. I'm your host as always, Leslie Eisted, and in today's episode, by popular demand on Piazza, that is the poll result, we're actually going to talk a bit about networking and how it kind of integrates with your operating system and at what levels of your operating system. It is meant to be a very, very high level overview. We are glossing over a significant amount of details. But if the topic interests you, of course, there is CS456, which is networking, and you're, of course, welcome to take that. And many people have taken that in the past. If you're wondering, did I take that as an undergrad? Actually, I didn't. I never took networking as an undergrad. Although kind of ironically, I did teach it a couple years ago. That was fun. That's always fun to teach something new. So there's no readings associated with today, but a few things that I do want to remind you about. Of course, the reading assignments are over with now, so hopefully you were able to submit that. The other thing I wanted to remind you about is don't forget about the quizzes that are on Learn. They are due very, very soon. Let me just quickly look up the date. I know I look it up like every time, but I forget every time. Why am I so forgetful? I'm forgetful because I'm trying to also get 2 papers published this month. So there you go. Now you know. It looks like they're due on August 5th. So that's in 2 days at 11:30 p.m. And that's going to be Eastern Standard Time or whatever that time zone is that I'm in. So I see that the majority of the quizzes had not been completed by most people, so please take an opportunity to do them. And for those of you who are wondering what is the weight of each quiz, it's the same. So even though each of the quizzes might be out of a different value, the weighting of each quiz is actually the same. The other thing I wanted to mention is I know in my last episode I mentioned that final exam has 2 attempts. Someone pointed out to me that on the website we had forgotten to update it and we had said there were 3 attempts. Now obviously that's not very fair to you guys for the website to say one thing and for Learn to say something completely different, even though they've both said those things from day one. Since we forgot to update the website, and it was an oopsie, I've adjusted Learn so that you now get 3 attempts for the final assessment. So that means that there are 3 attempts, just like the course website indicates. The reason why we had changed it from 3 down to 2 is based on all of the previous online offerings. I had observed that everybody tried it once, and maybe about 40% of students tried it twice, but there was a very, very negligible percent, if I recall correctly, that actually tried it the 3rd time, which is why I had originally decided to take it down from 3 to 2. But you know what? The website said 3, whatever. It's 3 now. It's not a big deal. And if you want to use the 3rd attempt, it's now there for you to do so. All right, so that's it. And another question I saw online, so I'm just going to try to refocus my camera here. You're going to put something in front of it to force it to refocus, which is kind of weird, but anyways. So the other thing people were asking is the final exam questions coming from the quiz questions? No, it's from a completely unique database of questions, and it is a database, so everybody's going to get a slightly different paper. It's entirely possible that you will get some questions that are the same between each attempt, but don't anticipate that it's going to be 100% identical. The database is actually divided for fairness into different types and different difficulty levels of questions. Because if we just had one big pool and said, okay, choose X questions from this pool, then somebody might get a significantly more difficult final assessment than somebody else. So to make sure that it was maximally fair, everything's kind of been divided up by difficulty and question type, and everybody will get the same number of questions from each pool. So that was our attempt at making sure things were fair. It's an open book. I'm not going to use proctoring software because I think that's an invasion of both your personal privacy, cameras and microphones and things like that, but also being an invasion of your computing privacy. We don't use any kind of proctoring toolkit. So we are asking you on the honor system to please don't create a Discord server and sit there and all do the exam at the same time together. I'm sure it happens, but whatever. Just don't do it. Please don't. But you can use the lecture notes, you can use the videos, and you've got like almost 2 years of videos at this point. So you've got lots and lots of content that you can actually use while you're writing the assessment. Again, you are going to get several attempts. The assessment opens up at 12:30 a.m. on August 7th, and that will run until 11:30 p.m. on August 16th. So you've got a good period of time to actually do it. Flexibility so that you can fit it into your exam schedule however you need to. And if your internet goes down, since you get multiple attempts, you don't have to worry about it so much. Yeah. And the reason why we've tried to make things flexible, again, is because I don't know what other courses that you're taking. One of the nice things about being in person and having the registrar's office schedule final exams is that we would know the probability of you having 2 exams back to back or 2 exams at the same time slot is almost 0. But with this online or even like a hybrid term, we have no idea what other courses you're taking. I have no idea what time they're scheduled for. I don't know when their final assessments are, and hence why we just said, write it sometime in this period, whatever works best for you. We're not trying to stress you out here. And again, the multiple attempts is because I'm going to assume you all live in the middle of nowhere and you all have crappy internet. And I make that assumption because that's what I grew up with. I lived in the middle of nowhere with crappy dial-up internet. So I'm going to assume you have the same thing right now that I had growing up. And I understand that there's probably like a 25-year difference there, but I think you get the point. There are still places in Ontario where dial-up internet is faster than anything else, unfortunately. And there's no cell service either. So I do know it is possible. All right. So that's kind of everything about the final assessment. I don't really feel like there's much else to say about it. You are going to need to do calculations and things like that. If you have a question about one of the questions on the assessment, you are welcome to post it to Piazza privately, but keep in mind that we are not on Piazza 24/7, so you might have to wait to get a response. If you want a faster response, your best bet is email, but even then, I'm not always sitting in front of the computer as much as you might think I am. I have other things I need to do. So we'll do our best to respond to questions, but again, make sure if you're posting questions, make sure they are private. Yeah. The other thing, I think I have some comments from the previous term. I'll try to post some hints to Piazza about answering some of the questions just in case they come up, like what format your answers should be in. So hopefully that will be helpful. I'll try to do that today. I'll make a note. I'll make a note right now to tell myself to post final hints formats to Piazza. There we go. I've made a note, so I will make sure that gets posted. So that make sure you read that before you write the final assessment so that you know what to do. The other thing is for any kind of numerical calculation question, it doesn't have to be exact. So don't worry about how many digits of precision you're giving because we actually have like a little epsilon there that if you're within this epsilon, then we'll assume you're correct. So don't worry too much about how many digits of precision do I need. We're a bit more flexible than that. All right, then. So we actually don't have an OS of the day today because, I don't know, we've covered all the really interesting ones. I mean, we could have talked about WebOS, but I don't really find it that interesting. We could talk about OSs that don't have users, but I decided that, you know what, let's just talk about networking today, and then we'll have a fun end video. It took me forever to get working, but have some fun with that afterward. I mean, my original plan was post-credits. I was going to fire up Red Alert 2 inside of Linux and just like play a skirmish or something live, but yeah, I couldn't get working. And last time I tried, I actually pooched my Linux installs, so that didn't work so well. All right, anyways, let's go on to networking then. Let's make this nice and big. Our slides are normally made in LaTeX, so these ones are not. So if you're wondering why there's a bit of a format difference, that's the reason. All right, networking and your operating system. I'm going to assume that actually the majority of you know a fair bit of networking. But to tell you a little story, when I was in undergrad, I didn't know anything about networking. It just wasn't something that interested me. When I was in undergrad, there were two things about computing that I was super, super interested in. I was interested in compilers and compiler development, and I was interested in computer graphics. But networking was not really something that interested me. And maybe you know this logo, maybe you don't, but this is RIM, which is now known as BlackBerry. But RIM, actually, all those buildings, if you remember, between Phillips Street and Ring Road, actually were all big RIM buildings. Like, they were built for RIM. The University of Waterloo actually used to be surrounded pretty much by RIM. And they donated lots of money to the university and various programs, and they hired a ton of co-op students. And I know they still hire co-op students, but probably significantly fewer than they used to. You know, BlackBerry kind of lost. But the story I want to tell you about RIM is that, everybody wanted to apply for RIM. Everybody wanted that job. And I always applied. There was either a compiler job that I was applying to or a graphics subsystem development job I would always apply to. And what was interesting is I always got an interview for these positions. And I'd think to myself, okay, well, it's going to be questions related to, compilers or questions related to graphics. And every time I would show up and the questions were about networking. And they would always ask the same question. When you type a URL into your web browser, what happens? And I would always give them kind of this look like, I don't know. And that's the truth. At the time, I had no idea what would actually happen when you typed a URL into your web browser and hit go. What would actually happen? I didn't know. Needless to say, I never actually got the job. But the thing that always amused me was the fact that I would apply term after term after term, and they'd keep interviewing me for this position, and they'd keep asking the same question, and I still didn't know the answer. I mean, it's weird that they would do that, but it's also weird that I probably didn't learn that. I have learned since then, obviously, a lot about networking, and I've done a lot of network developments for different graphics applications, but at the time, I didn't know. Now, there's lots of different models for networks. There's a 7-layer model, and there's a 5-layer model. I kind of prefer the 5-layer model, and I want to say that these models don't really reflect reality. I mean, when you think of something that says, this is a 5-layer model, you think to yourself, there is a distinction between layer 1 and layer 2, and there's a distinction between layer 2 and 3, and 3 and 4 and 4 and 5. But the reality of it is kind of blurred. There are things from layer 1 that kind of sift into layer 2. The lines are not so well defined, and a lot of things that exist in one layer also exist in the others. But I want to talk today just about the 5-layer model because it's the one I prefer. And the 5-layer model can be broken down into these categories. So there's an application layer, and that's the highest level. This is what you interact with on a daily basis. So if you are watching this live stream, you are interacting with the application layer directly. So you're on a web browser and you're typing things in and things like that. Sitting below that is the transport layer. And if you've ever done any development or created any kind of network application, then you probably have interacted with that layer as well, because that's like the sockets. And if you're doing any kind of socket programming for network development, then you would have interacted with the transport layer. But the layers below that are, for most application developers, would be unusual to interact with. Things like the network layer, the link layer, and the physical layer. And we'll go into greater detail what each of these specific layers are doing and what role or where they would live inside of your operating system. So to start with the application layer, this is the user program. So it's Chrome, it's Firefox, it's Netscape Navigator, it's Opera, it's Mozilla, it's Lynx, whatever tool you are using to interact with the web, that is going to be a part of the application layer. It's things like accessing web pages, playing on Discord, watching YouTube. But the application layer actually contains more than that kind of thing. It's also containing protocols, which is kind of like a standard form of communication. So you can think of a protocol as like if you were to greet somebody, to meet somebody for the first time, there is a certain polite protocol that you should follow to introduce yourself to them. You don't show up and say, give them a high five and say, yeah, what you up to today? I mean, you shake their hand, you say hello, you introduce yourself, you ask their name. There is a protocol for polite interaction, and there are protocols that live for internet applications, web applications that live in the application layer as well. So that's protocols for email and file transfer and BitTorrent and things like that. So things like HTTP, which is getting information from a server for your web page, FTP, which is usually used for file downloads, and then you've got things like SMTP, which is for email. Yes, lots of acronyms in networking. So many acronyms. Don't ask me what they stand for because I'm terrible at remembering what acronyms stand for. But that's why you have the internet, right? So you can look it up. So all of those different protocols are application level protocols. They are letting an application on your side talk to an application on the other side. And it's just, again, the protocol is just a prescribed way of communicating such that both the sender and the receiver are able to understand the message and carry out whatever instructions are in that message. So we said that the application sends and receives messages. Now, in terms of your operating system, where does the application layer live? This lives in user land. I mean, Chrome is not a part of your kernel, unless maybe you're using Chrome OS, but it really is a part of the user programs. So these different tools do not have kernel privileges, and any kind of access they want to lower level kernel functions are going to happen through system calls. All right. So what do you have below the application layer? So you have the transport layer below that, and that's actually responsible for sending and receiving the data for the actual applications. So the applications use their protocols like HTTP to format a message to say, please get me the following web page on the following machine. And then the other machine will say how, oh, I see you would like this web page. All right, here is the data and I shall send it back to you. So that's what the application layer is doing. But the application layer is completely uninterested with how the message actually gets sent. I mean, they just want to eat the sausages. They don't actually care how the sausage is made. It's a really weird analogy. So it's the transport layer that takes the messages from the applications themselves and tries to, and is responsible for sending and data and receiving the data for the applications. So the messages are from the application, and the transport layer is going to be the postman. So the postman takes the message from the application, and it's going to hand it off to the postal network. And the postman is then going to receive the package from the postal network and hand it to the application. And I tend to use a lot of postal analogies when talking about networking because I think there's a lot of similarities between the two systems, but also because my grandfather was a mail delivery and my mother-in-law, a lot of people in my family deal with the mail system. So I've seen a lot of it. Now, there are protocols that actually exist at this level. And in fact, in the network model, there are protocols at every level. So many of them. But at the transport layer, the two protocols that we see are TCP, which you've probably heard of, and UDP. Again, I'm horrible with acronyms. I actually wrote them out here because I knew I wouldn't remember. TCP, Transmission Control Protocol, and UDP is User Datagram Protocol. These two are things that if you've ever done any kind of socket programming or network programming, you would be familiar with these two words. Now, what is the difference between these two? So TCP is a reliable protocol. It's the postman that takes your package, puts it into the network, and then when it gets a response, it gives it back to you. And if you send 6 questions out the door, the postman makes sure that those questions go out in order and that the responses to those questions are received in order. So you're not going to receive the answer for question 5 and then question 2 and then question 6. So TCP is guaranteeing but the messages from the applications actually get received, but it's also going to make sure that things are in the correct order. And that means, that's why we call it a reliable in-order transmission protocol, because you can be assured that if you send it by TCP, you will get a response and it will come back in the right order. This actually comes at a bit of a cost, because we have to then check, okay, did the package actually get received? And if it didn't get received on the other side, so we have all this validation going on, then we have to send it again. And we have to keep sending until we can guarantee that the recipient has actually received it. And then we have to wait for the response in order. And we can't even really ask the next question until we have acknowledged that the recipient has received the first question. So TCP has a fair bit of overhead to guarantee that reliability and the in-order transmission. But it is also the most commonly used protocol on the internet right now for transport layer. And that is because we generally like reliability. So things like if you're watching a movie, you kind of want the movie to be displayed to you in order. Now, what's interesting is we don't actually use TCP a lot for streaming anymore. We use this other thing called UDP. Now, UDP, User Datagram Protocol, I hate acronyms, is unreliable. It does not guarantee. It's the postman that picks up your message, tosses it onto the truck, and hopes for the best. Like literally like, here you go, I'm going to hope for the best now. And it doesn't care what order responses come back to you in. It's like, oh, look, you got mail. Here you go. So UDP is unreliable and has no guarantees of order in the order of transmissions. But as a result, it's much faster because it doesn't have to do all this validation that the other actually received the parcel and so on and so forth. UDP is becoming more and more popular. So things like HTTP, email, FTP, file transfers. Traditionally, these things have all used TCP so that you can guarantee reliable transportation of data to and from a server and a client. But as of recently, people are exploring, can we use UDP for this stuff? And so we're starting to see, I think, one of Google's experimental new versions of HTTP might actually be using UDP, which is kind of cool. And some web streaming services may also be using UDP. Now, you can get away with this. You might be thinking, well, if it doesn't guarantee arrival or if it doesn't guarantee, in-order transmission, well, what happens if you're streaming a movie and you get data packet 6 and then you get data packet 5? Well, if you're already watching data packet 6, because let's say you don't wait for data packet 5, you just move on to data packet 6. Well, if you're watching data packet 6, why would I then go back in time and show you data packet 5? So the video might be a little bit jumpy because it might be missing small data packets, but at the same time, once the other ones arrive, we can just toss them out. It's just a thought. Now, a long time ago, I actually, I guess this wasn't that long ago, from my perspective anyways, one of the things that's kind of interesting is, so I was developing a tool to send motion capture data from a mocap volume into Unreal Tournament 10, 11 years ago, before it was directly supported by Epic. We were trying to do that, and originally we were just using shared memory. So we were just using interprocess communication, simple shared memory to do this. The problem was that the machine that was running the motion capture software and having that machine also drive Unreal was kind of unrealistic in terms of performance. So we wanted to then send this between multiple machines, so we thought, let's use a network. And we had to make the decision, do you use TCP or do you use UDP? At the end of the day, we did end up deciding to use TCP because of its reliability and in-order transmission. But we could have probably gotten away with UDP, I think, at the end of the day, simply because if we receive frame data after we've already shown that frame, like the preceding frame, then we could have just tossed the information. There are ways we could have handled it. Now, it's really interesting. So TCP has all that reliability built into it. UDP has none of it. But what you will actually see is application protocols will actually build some of that reliability. So they will do their own checking and their own in-order transmission retrievals for on top of UDP. So it gives you the choice of doing it or not. Now, where does TCP, UDP, and everything in this transport layer actually live? Lives in your OS. Lives in the kernel of the operating system, which is kind of interesting. Now, what we have is when we want to use something like the TCP or UDP protocols, what we are going to do is we create a socket. We create a TCP socket, or we create a UDP socket. Creating a socket is a system call. The implementation of these libraries, the implementation of the sockets, actually lives in the kernel of the operating system. And so we are making system calls when we are creating these sockets and so on. And we'll actually show you some of this later. Okay, then we have the network layer. So this sits below the transport layer. And this is a different kind of postman. This is the truck. And the truck is going to take the mail from the postman, and it's going to drive it from, it's going to arrange to have it driven from the origin house to the destination house. So you've got the application layer, which is like, it's going to address things according to the room in the house or the individual's name in the house. And the TCP layer is responsible for making sure that mail that arrives at the house goes to the correct person. Well, the network layer is going to make sure that mail that goes or comes from this house goes to the correct other house. So the application layer is labeling the actual recipient. And then the transport layer makes sure that mail goes to the right application. And the network layer makes sure that mail goes to the correct computer. Now, there are protocols that exist within the network layer, and that is the IP protocol. You've probably seen the words TCP IP. It's because it's TCP on the transport layer and then IP on the network layer. There are other protocols on the network layer, but they're not so common. IP is the most common, and this is actually used to send the applications from one computer to another computer. And so let's talk a little bit about addressing here for a moment. In the application level, we are going to need to create an address for this application. And we create the address for the application using the transport layer. The transport layer gives each application or each internet connection, each socket, a port number. Think of it as the room number in your house or your name. And so once mail arrives at your house, we need to know to which application to put it. Well, the port number tells us to which socket we need to deliver that to. The house address, your computer address, is the IP address. And that could be IP version 4, or that could be the IP address version 6. If you're wondering why do we have version 4 and version 6, it's because we kind of are running out of the version 4 addresses, so we need bigger ones. Hence why we have version 6 ones. All right, now there are other protocols that exist at the network layer. There's this ICMP, and ICMP is actually used to send error messages and control parameters. So to tell destination machines, hey, I didn't receive this, or hey, this was garbled, or if you want to send some control information from one to the other, you can do that via the ICMP. And there's lots of other protocols that exist here, but these are the two big ones that exist. Okay. Now, if we go down a layer below this, so we're able to collect data from applications and we're able to send it out the door to the destination machine. But how does my computer here know how to send it to your computer over there? I mean, really, the network layer just says, oh, and this is the destination IP address. Okay, I'm going to close my eyes and I'm going to throw it out the door. Okay, so how does it know then to go from you to the other computer? How does it know what path to take? That would be the link layer. So here's the thing is your computer might actually have several different what are known as NICs or network interface cards. The computer that I'm live streaming from has 3. So it's got a Wi-Fi one, and it's got a 1 gigabyte one, and it's got a 2.5 gigabyte one. So I've got 3 NICs here, but I'm only using one of them. So this is going to, so even though all of those different network interface cards, they all live in the same computer, so they all have the same computer address. But I'm actually sending them out a very specific door of my computer. And those doors are labeled with MAC addresses. And I'm sure you've seen MAC addresses before. They're those funny little 2 digits, colon, 2 digits, colon, 2 digits. You know what they look like. You've seen them. And it's the link layer that is actually transporting data over the postal network, so over the actual network. So it's actually sending data from this machine to the next node in the network. And actually, it's between the network layer and the link layer that we actually create the paths, to go through the internet from my source to the destination. So from the sender to the recipient. We're going to create a map and we're going to send it. And to know exactly the path, we use these links. So each of these, when we arrive at the next node of the network, we have to compute, okay, well, which is the next node of the network I should be sending it to? So in my home network, which is not really looking like a home network anymore, I think, I don't remember which of my systems this one's actually plugged into. So I've got some 10G switches and I've got some other switches which aren't 10G. But I'm pretty sure that mail from anything message going out from this desktop here that I'm using right now goes to my primary switch because it's on the network. And I think that's the one that has a few 10G ports, but I think it's just on a 1G port right now. I think my other desktop's on the 10G port. So it's going to go from here to my primary switch. And I say primary because you're like, wait a minute, does that mean I have more than one switch? Yes, I have more than one switch in my house. I think I have like 3 or 4. Don't ask. So it's going to go to my primary switch. And then from my primary switch, it goes to my router. And then it goes from my router to my cable modem. And then from my cable modem, it will go out into, finally leaves my local network and goes out into the world. But the path it takes is between all of these different network interfaces. And so we are actually plotting this path through all the different nodes of the network. And what's really interesting, if you take 456, is you'll actually learn about how you plot these paths. And then you learn about, well, what do you do if there's multiple possible paths? And this is where stuff gets so crazy about networking. The path that your data takes through the network, and there's always multiple paths, isn't necessarily going to be the fastest one. You might be like, what do you mean my data doesn't take the fastest path through the network, even if it's known? Well, politics gets involved, and yes, politics gets involved in your network traffic. If there's 2 countries that don't get along, they may not allow packets from your country to travel through their country. And so you might have to take a longer path due to this. And it's crazier than that, because then there's like different, these nodes are owned by different companies. And so if you want to travel through parts of a network, your network provider might have to pay to send it through there. And if they have an agreement, it might be cheap. And if they don't have an agreement, it might cost too much money. So they might take a slower path just to save money. And it's just, I mean, there's the optimal path, and we know how to find it. We know how to map routes through the internet. And then when politics and money start getting involved, it starts to get really, really crazy. But anyways, take networking and learn all about it, or you can find the textbook on the internet and read it. It's kind of an interesting topic, actually. The link layer, anyways, is what's actually sending the data between each of the individual nodes in the network, each of the ports. And there's lots of different protocols, obviously, that exist at this layer as well. So, for example, Ethernet. Now, I know a lot of people, when they hear the word Ethernet, they think of the cable, like a Cat5 cable or a Cat6 cable. Ethernet is not a cable. And it's so easy because, I mean, I always consider, if I'm going downstairs to my cable box to pick up a cable for my network, I don't think to myself, oh, I need to pick up a Cat7. No, I'm thinking to myself, I need an Ethernet cable. But no. Ethernet is a protocol for transmitting data between two nodes of the network. And then there's protocols for Wi-Fi as well, and so on and so forth. And you've probably seen this diagram before. There's all different kinds of protocols used for Wi-Fi. All right. Below that, we have the actual physical layer, which is the actual hardware and the actual transmission of bits. And this has crazy stuff living down here as well, because it's not so simple. For example, if you are on a ring network, you can get collisions of packets. So one machine sends a message and another machine sends a message. There's the possibility that there's a collision between those two signals. And one of the interesting things about signal collisions is they can behave in such a way that they actually cancel each other out and both messages are totally lost. It's as if they neither of them existed. So on the physical layer, when we're actually transmitting the bits, there's all kinds of different methods to detect signal collisions, recover from signal collisions, prevent signal collisions. There's multiplexing, which is how do we make it so that we can actually send multiple messages at once. There's so many interesting things that actually live down here as well. But all of these things, so the transport layer, the network layer, the link layer, and the physical layer, they're all kernel side things. So the transport layer, that's going to be in the kernel, so you need to make system calls to create the sockets. The network layer is going to live further down into your kernel. The link layer is actually going to be part of your kernel, but also part of the drivers for the individual devices. And then the physical layer may be something that's implemented on the physical hardware itself. All right. So just to review the kernel's role in this. So application layer, user program. Absolutely user program. Sockets, the transport layer, which is the label we give to each application that's trying to send or receive a message. They all live inside the kernel. And when you want to create a socket for an application to send data, you are making a system call to request that socket. When data arrives at the machine, so this is how things are going to work. So let's say you are receiving a message. So the physical layer delivers the message across the wire or through the radio waves to a network interface card. So, and the link layer helped to make sure that it arrived at the correct network interface. And then the link layer is going to pass that to the network layer to validate that, oh, did we arrive at the correct machine? Okay, we're at the correct machine. So this message is for us. And then the network layer is going to pass that up to the transport layer, where the transport layer is like, okay, I have a message. Which socket is it for? And the transport layer is going to take it and put the message into the correct socket so that the application can then be notified, hey, you have data for you. That all happens inside the kernel. All of that is happening in the kernel of your operating system. So just an example here. So this is creating a socket, And again, this is all happening by system calls. So this is just a very simple pseudocode to create a socket and listen and then send a message. So what we've got first is this command here that creates the socket. This is a system call that creates a socket in the kernel for this particular application. And you can have multiple sockets, by the way. An application can absolutely have multiple sockets. And when you, oh, jeez. That was funny. When you have these sockets here, you can, it's creating a labeled door in the kernel, so that when messages are sent from that labeled door, they know that the sender was this labeled door. And then when you receive messages that want to go to that port number, which is the label, then we know to send them here. So this is a system call to create the socket. And then the bind command is going to create a TCP socket. And a TCP socket is what's known as a connected socket. So when you create the socket door, you have to bind it. And what the binding does is it's like creating a pipe, like a tunnel that goes from this socket door on your machine to another socket door somewhere else. And data that goes over between those two sockets can only go through to those two destinations. So you can't, through this socket now, send data somewhere else because it is bound to those two doors. And any data that goes out one door must go to the other door and vice versa. So a connected socket is, we're creating a socket that is bound to a destination address. Everything that goes out this door goes to that destination. And that means that any messages you send, you don't have to tell it where to send them because the socket already knows where to send them. By the way, UDP, you don't have to create a connected socket. With UDP, you can just create a socket, and each UDP message that you send, you can actually just say who you want to send it to. It doesn't have to be connected to somebody on the other side. Now we have this command called listen, and this is a blocking system call. So this user application is going to be blocked until a packet arrives at this socket. So we are listening for data to arrive at the socket. It's kind of neat, right? I think it's kind of neat. And then we have another blocking system called send, and this is going to block until this message has been successfully sent. Once the message is sent, the thread wakes back up. Again, these four things are all system calls. Every single one of them. Yes, networking can be expensive. So as I said before, that was the transport layer, creating the sockets, showing you the different system calls. The network layer is also a part, and the link layer is also a part of the kernel. They are absolutely down there. And I know I keep referring to everything as packets, but just for the record, yeah, there's a different name for everything on each layer. So for example, in the network layer, we call it datagrams. In the, I think it's the transport layer, it's packets. And then it's messages, as I said, and then in the link layer, they're called frames. Everything has a different name. So the network layer is going to, whenever data arrives at the machine, the network layer is going to pass it to the transport layer. And again, this happens in the kernel. And the transport layer is going to look at that port number and deliver the message to the correct socket. And when you deliver a message to a socket, you're probably going to wake the waiting thread up from the user program. And what that really means, you might be thinking, oh, it's going to wake up and start running. No, it means you're going to move that thread from that user program to being from the wait state, you're going to move it to the ready state. So it's kind of cool, right? All right, now what else does that network layer do? It's going to take the packets from the sockets when they're being sent out. It's going to convert them to the datagrams for the network layer, which involves usually splitting them into smaller pieces because TCP and UDP sockets allow much larger packets of data than the layers below it. So we're going to subdivide it into smaller pieces, and then we're going to wrap it in a new piece of wrapping paper with a new destination and source address because we don't care about sockets at this point. And then we're going to send it down to the link layer, which again is going to live down in the kernel, but partially on hardware. And the link layer is going to further format those datagrams into frames. The frames are specific to the protocol you're using within the link layer. So that's kind of fun. All right. What sits below that? Well, there's lots of different things that actually happen. Lots of other protocols that exist. And parts of this actually exist in your kernel. They don't have to, but some of it does. So one of the jobs that we have to do in the network in the link layer is routing and forwarding. So that is, how do you know if you're at this particular node in the network? How do you know whether you should go this path, the upper path to the destination, or the lower path to the destination? Or how do you even know these paths exists? So we have all these things called routing tables and forwarding tables, where we know that if your destination is this, then you need to go through this particular path. And if your destination is this other one, then go through this other particular path. And the kernel can actually participate in these different routing algorithms by holding on to some of these routing and forwarding tables for things. And again, these are used for how do you direct traffic through the network. Now, something else that your kernel may play a role in is something called the ARP protocol, or the address resolution protocol. So your kernel may maintain a map that maps the MAC addresses of the individual network interface cards to their IP addresses. So for example, when in the link layer, we're transmitting data from network interface to network interface. But sometimes we need to know, okay, well, what's the actual IP address of this network interface? Sometimes we have the IP address, but we don't know the MAC. So we have to look these things up, and this ARP table will map those MAC addresses to IP addresses so we can actually do that lookup. And if you actually look at your network traffic, you'll actually see things like that. I'm going to try to show you that, but I can't promise because I'm not sure I have Wireshark set up properly right now, but we'll try to look at that. Another thing that your kernel actually participates in is packet filtering. So when data arrives at your computer, you can choose to throw it away. So it's part of a firewall. So let's suppose you know that a certain website or a certain mail coming from a certain IP address is spam. Let's say you know it's part of a denial of service attack on you, and you know that these people are using this IP address to send these nefarious packets from. You can actually, through the settings in your operating system, you can actually tell the kernel to throw them away. So if the destination or the source is from a certain IP address or a certain range of IP addresses, you can have your kernel toss them away. That means the second they arrive at the network layer and we're looking at the source IP address, we can say, oh, this is not an IP address we actually want to receive from, so we're just going to throw it. We don't even bother passing it to the socket layer or the transport layer. We're just going to toss it right away. And you would use system calls usually to add entries to the packet filter tables. And now, why would that be in the kernel? Why would you need system calls for that? Well, you need to tell your network interface, the network layer, to throw things away. And that's going to be part of your kernel. You don't even want to get it to the socket layer. You don't even want the applications to know those packets are arriving. Something else that the kernel occasionally participates in is network address translation. Now, this one's really interesting. So, have you ever noticed what the IP addresses are on your own computer. So I'm just looking here. I want a command for my terminal. I never remember a lot of these commands. So let's open a new tab. Let's grab that. Let's make the text a little bit bigger and we'll get out of this crazy directory here. So if I type ifconfig-a, it tells me all sorts of information about this particular computer. So it tells me all of my, well, it looks like it's showing me 4 NICs, and so network interface cards. And then it's telling me the IP address and the MAC address of each of them. So I've got like a MAC, and then I've got some IP addresses here. So it's my local IP address. Now, you might have a computer on your network that has the exact same IP address. And I bet you do. If you have like 7 computers on your network. I don't know how many I have. I have so many devices on my network, it's starting to get a little crazy. But that's my local IP address. But you can't type that SSH 192.168.1.7 and you can't SSH into my computer. If you tried to do that on your network, the machine either doesn't exist or it logs into one of your own machines. So what's going on here? So the truth is that certain ranges of IP addresses are actually reserved for different purposes. And that the ones that start with 192 are reserved for local networks. So your own personal network. So in my house here, I have 2 desktop computers, 2 Apple laptops, 3 Microsoft products. Trying to enumerate this. Every light bulb in my house is on my network. Now you're probably confused. Why are your light bulbs connected to your network? So I can turn them on and off without actually getting out of my seat. Everything in my house, even my furnace, is connected to the network. So I have all of these devices. When I am, and what's fun about them is, if I'm driving home late at night and I forgot to turn the outside lights on before I got home, while I'm in the car, I can turn the outside lights on in my house. But wait a minute. How do I communicate with the outside lights in my house when I'm not on my local network? So if you send a message from the wide area network, so just out in the wild, to your home, how does it know to send that message through your router to that specific device? And that's what the network address translation table, the NAT table, actually does. Is the NAT table is going to, so we actually map IP addresses on your local network to port numbers. And so when a message arrives at your router will look it up in the NAT table and say, oh, this message here was actually meant for this device here. So it will repackage the packet with the correct destination on it. Because the data arriving at your local network, you only have one exterior IP address for your home. And it will know, the NAT table will help map those to the correct devices within your home. So that's actually a really cool thing. Now, there's lots of other networking different protocols and tools that exist but aren't usually a part of the kernel. So there's things like DNS caches. What's a DNS? So DNS, that's a really important thing. And it's amazing how much network communication actually has to happen before you can actually view a web page. The first thing that actually has to happen is we have to translate the URL, the human readable URL like Amazon.com. We have to translate that to an actual IP address because the internet does not speak strings. That's for humans. Those strings, those URLs are for humans. The network itself doesn't speak that. The network itself speaks in terms of MAC addresses and IP addresses. And what DNS does is it takes that URL and it does a lookup. And it looks up what is the IP address for the URL that you're trying to visit, and then it passes it back to your computer. And what can happen is you have this DNS cache, so that each time you don't have to go ask the DNS network. You have local caches. You can actually have a cache right in your house. You can have your own DNS cache. But usually it's done at like your ISP level. So your ISP, maybe you have Rogers or Bell or TechSavvy or Earthlink or who knows what you have. They will have their own DNS cache. And so when you make that URL request, a DNS request, it goes to the cache first. And if they know it, then they send the answer right back to you. And that's faster than going to have to go further up the tree to find the actual answer. So DNS caches are out there, but they do not have to be a part of the kernel. DHCP is another one. You might be familiar with DHCP. You know, when I first started with network computers, you got a specific IP address. Every machine was statically assigned. It had an IP address. It was fixed. But that's not how we do things anymore. Like, even your router at your house changes its IP address from time to time because it's assigned via DHCP. It's whatever IP address is available, it just gives it to you. So what would happen, you were like, well, how do you send things from one computer to another computer then if it doesn't have an IP address? Well, the machine, your DHCP server machine, which is usually your router, will like broadcast, hi, I'm the DHCP server. So when you plug your computer in and you say connect via DHCP, you put out or you see that message. You're like, oh, cool. That's the address where I can get my own IP. And then you send a request to the DHCP server and it will give you an IP address. So that's kind of neat, right? And then there's lots of other really cool things like ping and traceroute and all different kinds of network diagnosis tools. And those are usually user side. And they're kind of fun. I'd like to show you some of them, actually. And again, I'm not sure all of these will work, but let's give it a go. Because I'm pretty sure that Wireshark wants something from me that I don't want to give it. I don't know, that's it. Okay. Well, let me just log in here. There we go. So let's grab this one. There we go. Whole bunch of lovely data. But what this tool is, this is Wireshark. And again, this is an interesting tool. This is a packet sniffer. It's very legal, by the way. And what this lets us do is actually monitor all of the packets that our network interface. And you'll notice I chose a specific network interface. I chose a specific card to listen to all of the traffic that it sees. And you can actually see all of the different kinds of protocols here. So we've got some TCP protocols, lots of TCP, this RTMP, which I'm not familiar with. What I'm finding odd right now is I'm not seeing any ARPs. My network is usually so full of ARP requests, it's hilarious. But if there was UDP going on here, you would see that too. So you can actually see the source and the destination for each of these different messages. It's pretty cool, right? And what's really cool, so this traffic here doesn't actually look that noisy because I'm connected over a wire to a switch. And so I'm only going to receive two kinds of traffic. I'm going to receive traffic that is sent to everybody, but because I'm on a wired connection, there's not going to be a terrible lot of that. And I'm only other than that going to receive messages that are sent directly to me. Now, I'm actually not connected to a wireless network here. But if you're connected to a wireless network and you run Wireshark, you're going to see all kinds of stuff. It's kind of cool, actually. So what's interesting about wireless is it's not a message from one server going directly to you. any messages that are sent from the wireless router out actually go to everybody. And then it's up to the link layer and the network layer to decide whether that message is actually for you or not. And if the message isn't for you, it discards it. But the packet sniffer still picks it up, which is kind of cool. So what's interesting is when you, like if you were sitting in the middle of MC and you're connected to Eduroam, run Wireshark, and you can see packets going to everybody in the room because everybody gets everything. And most of the packet data tends to be encoded or encrypted in some way, but not always. A lot of data actually gets transmitted just plain text, so you can actually, sniff and snoop on what some people are doing. Not that I recommend it, wireless is not that secure. You can see everything. So that's kind of a really fun tool. And again, that is going to be using system calls, but the Wireshark program itself is a user program. What other cool kind of networking monitoring tools live in userland? Well, of course, there's ping. Everybody knows ping. So if I want to ping, say, the Google, so I can do that. And what ping does is it sends a sequence of small messages out to the server and waits for responses. And then, so you can see here, it's just a 64-byte message. Now, how did it know to send it to 142.251.4178? That's the DNS lookup mapping google.com to this actual IP address. And you can see here that it's actually sending this data, and then it tells me how long it took the Google server to actually respond each time. That's a really cool one. So here's something really neat. Another really cool tool we can use is called traceroute. What traceroute is used for is to actually send or to actually track the path that your parcel takes through a network. And it will tell you how long each of those things do. So what's really neat here is we can do traceroute. Let's just do google.com. Oh, see, I told you this might happen. I may not actually have everything installed. Let's get that installed. There we go. So here you can see we are tracing a route from my computer to Google's computer. And it's going to show us all of the little hops it takes through. So it's going, you can see here, this is the standard home router address. Yes, I have an ASUS router. So I'm going from my ASUS router, and then you can see I'm going through a number of routers in my local neighborhood. And you can see I'm going through three tech-savvy routers, and then I go through a bunch of things, and then finally, I make it to the destination. And you can see how long it takes to go from each little piece to each other little node in the network. So traceroute's really cool. Now, traceroute can also be used for identifying servers along the way if you want to attack a specific server or a specific router along the way. And so some people actually have their routers configured in such a way that they will ignore traceroute requests. And that's, if you ever see no response from a particular server, that's what happens. So that didn't take too long to go from, my machine to Google here. But what about if I wanted to send something to like Australia? So this is kind of neat. So I got to find an Australian university. Because I don't know anything about Australia, the universities. I'm choosing Australia because this is an interesting way to show you that it takes longer to send messages to Australia than it does to send messages to Toronto. And one of the reasons for that is because there is a cable that runs under the Pacific Ocean that carries network traffic from North America to Asia and Australia. And it's not free to send data over this long cable. It actually has a cost. So if we try to traceroute, this is going to take a long time, to anu.edu.au. So So what's interesting is you're going to see the same start. Oh, that was way faster than normal. But what you can see here is some really interesting ones. You can actually see that some of these are starting to take a really long time. So whenever we are going under the ocean, you're going to see that some of the transfer times are taking like 264 milliseconds as opposed to back here when it's like significantly less time. That's pretty cool. So yeah, traceroute can be used to actually track the exact path that your data takes through the network. So there's all kinds of really cool tools you can play with networking. All right. So that is my very quick introduction to networking and some of the different technologies that we have and where they live in your operating system, and some other little toys that you might have available to you to play with your network. That is officially then the end of the course, by the way. And there is no more. That's literally it. I know there's a slide here, but we already talked about it. So we are at the end of the course. I hope that you have found this course to be valuable or interesting in some way. I know that low-level programming isn't for everybody, but hopefully we got you through it and you're not too scarred from the experience. If you haven't filled out the course evaluation, please do. Again, this evaluation is just for what do you think of the online offering? I don't even see the answers. I think the school just uses it to make sure that the online offering isn't awful. Hopefully this hasn't been an awful experience for you. I hope that whatever it is you are doing in your next term, that you have a lot of fun and that you enjoy the rest of your CS program. And maybe we'll see you again sometime for some other course. You never know. All right, so that's it. We'll talk to you another day.